my title expanded ever so slightly. I threw volcanoes in there too, just to add to the crazy mix of subtitles in this talk with the dating game. Anyway, I'm Barbara Helmkamp. I have my PhD in physics from Louisiana State University, and that was a long time ago. And in the meantime, I've done a fair bit of teaching in various capacities, Lutheran schools. I'm online with a school called Veritas Scholars Academy right now. I teach some chemistry and some calculus. And anyway, so that's me. So now I just need to switch presentations from this to my other one. There we go. So, in the course that I teach, the chemistry course that I teach, uniquely, it begins with nuclear chemistry, even though it's a high school chemistry course. And it's a Christian school, and so I have this wonderful opportunity to help the kids understand the assumptions that go into the various radioactive isotope dating methods as I teach them about alpha decay, and beta decay, and gamma decay. And so to be able to do that as a creationist in a big school, it's really great fun. But that's the springboard for my talk this evening, is to maybe, I anticipate some people don't even know what I just said. I rattled off some things and it just went shoo. And then there's some who are very acquainted with the topic. But I think it would serve all of us well to review exactly what assumptions are being made with the various dating methods of rocks, and to understand also the very interesting research and creation science results that are related to these various dating methods. So I call this the dating game. I was going to make some quip about that, but because my daughters are both of that dating age, but I'm just going to skip that. So the pictures I have here, this was a presentation put together rather quickly, and I think I forgot the fourth thing I was going to put up there. So what would it have been? This is a halo. There's a zircon. There's a volcano. I don't know, something up there. A piece of coal. So to begin talking about how you date an object, determine how old it is. It didn't go forward. Well, that's strange. Well, that's very odd. Aha, yay! Okay, so just to think about the whole process, I have a map here. This is a drive we make fairly often because we have a daughter in college here, and we live here. And so you might say that it's a 13-hour drive. That would be, the analogy is that when we say something has a half-life, that's a time, but what we really mean is a rate. And so when I say it's a 13-hour drive, what I really mean is that we're going 60 miles an hour on the freeway. Because they're directly related given the distance of the 785 miles. And so because otherwise it's hard to think of a half-life as a rate. And you see this big number, and you immediately think, oh, old. When really it's just a rate. And so that's the first sort of idea I would like to get across. And so we see that a time here, 13 hours, is in the denominator, and the rate is up there. That's called inverse or indirect proportionality. So now what if I zoom in, and we're just at Des Moines, and we do the 114 miles in 104 minutes, we still get a mile a minute or so, and it's still 60 miles an hour. So the idea is that the distance coupled with, of course, with the time is giving you this rate. But we, again, have time down here and rate up here. So how does this relate to radioisotopes, they're called? Isotopes are elements are composed of multiple isotopes having different numbers of protons and neutrons in the nucleus. And so that's what that term means. When we speak of a parent, we're talking about the unstable isotope or nucleus that then decays. And so instead of distance, we have an amount. I have suddenly dry mouth syndrome.
So you're
Pardon?
saying parents are unstable and decaying?
Yeah, I thought about making that joke too, like along with the dating, but I'm not going there. So you have a parent is the unstable nucleus or unstable element, if you will. It's an isotopy element that is going to decay away. And you can sort of see what looks like exponential decay turn on its head just by following this that way. But the idea is that you start with an amount, and a half-life later you have half the amount, and 2 half-lives later you have a quarter of the amount, and so on. So again, the analogy to the travel is that instead of distance, we're talking about the amount. And so, for those of you who are of the math variety, we have now a rate, but it's a rate constant because this is exponential decay, but the idea is still here. Here's our rate. This rate constant is what's constant, and then this half-life ends up in the denominator over here. And so, just because this is big doesn't mean you need to wait that long to measure anything. That's a misconception a lot of people have. So, for example, instead of measuring half-life, you could measure 10th life. You could measure 100th life. You can measure 100, billionth life. It doesn't matter. After a 10th life, you decrease by a 10th. After 2 10th lives, you decrease by 2 tenths, so forth. So, and again, you have a different number in the numerator to make it all work out, because this is the same rate constant. You haven't changed anything, it's like whether you're measuring the distance from Des Moines to Iowa City and dividing by that time, or you're measuring the distance from Denver to Iowa City and dividing by that time, you end up with the same rate. And in this case, it's a rate constant because it's exponential decay instead of linear. So jumping from that now to a whole bunch of interesting decays, and this is what they look like. This might be really painful for some of you, and others you just say, oh, I know what that means. But let me try to help you. So the unstable isotopes are the ones with half-lives. So a material that doesn't decay has an infinite half-life. That's what it means. It never decays. So we have some very, very long half-life unstable things in our world. Elements, beryllium and uranium-238 are very, very stable, very close to infinite. So very slow to decay, very, very slow. And you can see we run the whole gamut. How do you spell gamut? I've always wondered anyway. Doesn't matter. The whole gamut from trillion years. This is the longest half-life of anything. Trillion times a trillion. It's 10 to the 24. It's a trillion is 10 to the 12. All the way down to, what would that be? Fraction of a second. And I have a couple of these decays in gray because they involve either the capture or the emission of an electron. That E is an electron. The others are all what's called alpha decay because they spit out helium. So you can see helium in all of those. And what the number that's up at the upper story in front of the element symbol is telling you the mass number, the total number of protons plus neutrons that define that isotope. So that maybe unpacks that a little bit. We're going to be thinking about these various reactions as I go through and talk about zircons and volcanoes and etc. So here, the periodic table of the elements, I think probably everyone can dig back far enough to a chemistry course where you saw this at one time in your life, right? Or else it's very familiar. That's how it is. So these are the various elements, there are isotopes shown that are involved in some of the things. So it's just some of the reactions we just looked at. So there's carbon and nitrogen. The red ones are my unstable ones. The blue ones are stable. polonium, uranium, thorium, potassium, even though it's a K, argon, helium. I should also have xenon and radon on here too, because they come into the fray as well. So a parent isotope is necessarily unstable, because otherwise you have an infinite half-life, and you don't even, why talk about a parent if there's not a child? You're not a parent until you have a child, so if you never have a child, you're not a parent. So parent isotopes are necessarily unstable, that's what it means, but the daughter that comes out might or might not be. So in these, I backed up one. Lead 206 is stable. Lead 210 and lead 214, Pb, it's Latin, right? Plum bum or something. These two are unstable, this one is stable, for example. Nitrogen 14 is stable, carbon 14 is not. Argon 40 is stable, potassium 40 is not, etc. So it varies. So here I brought my objects from my object lessons about the three assumptions, and we can think about this because it doesn't matter what timing device or dating device you use, they're always the same. So the classic one you've seen in many a creation talk, if you've gone to many a creation talk, is the hourglass because it illustrates it so beautifully. And right now all the sand has fallen through. But, for example, if I remembered to turn it over at the right time and we waited a while, then we'd see there's some amount of sand collecting in the bottom. So you might want to know how old the system is based on the amount of sand that's falling down into the bottom of the jar. How long has the sand been falling? So there are three assumptions. One assumption is that this is a closed system, and it's beautifully illustrated by the glass being closed. You'd mess up any ability to infer how long it's been, how old the system is since it was flipped over, if you had a little trap door that you could add sand to or remove sand from. So it's a closed system. That's the first assumption. The second assumption is that all those sand grains are distributed uniformly enough so that the rate, as you see the sand falling through, is constant. So constant rate is an assumption. And then the third assumption is that you knew what the initial state of the system was. That the assumption would be that someone waited for all the sand to fall through, and then they flipped it over. Okay? They didn't flip it over like, what if I flipped it over now, right? I didn't wait for the system to zero out. So those would be the three assumptions as illustrated by the hourglass. And so there they are. Closed system, known initial emissions, constant rates, even though I said them in a different order. A candle is another great example. So this is my Advent wreath, and then my tapers have gone down. So how old, if I need light candle, right? So anyone have a match? Let's pretend one of these, or they're all burning, if you will. We want to know how long they've been burning based on the height of the candle. So the same assumptions. We'd have to assume a closed system. So I wish it were burning so you could see it. We'd have to assume nobody came in and blew it out, waited 5 minutes, and lit it again. So in this system, the closedness would be no interference. A lot of times that translates into no contamination. When you hear the word contamination, that's somebody saying, well, we can't make the closed system assumption. Okay, that's what contamination means, that's what interference means, depending on the setup. And so that's the closed system assumption. The rate assumption is going to be that these candles are uniform in what? In diameter. Because the diameter is going to control how fast they burn down, as well as the wax type. So they all just have the same kind of wax. We have to assume that the pink doesn't change the wax, it's just pink. But they're the same kind of wax, and they're all constant diameter. But what are these candles called? They're called tapers. So a lot of them taper up small. So the diameter is changing, So that right there, you would not have a constant rate unless you have a nice square-topped candle like this so-called taper, this white one I've got here. And then the third assumption is initial condition. So was this the initial condition of all these candles? Were they that tall to start? You might think so, but actually I bought half-sized tapers. So these are a lot younger than it looks. So that's another example, another system. And then to think about the assumptions that go into being able to say how old something is. And another is back to the map. So how old is this system? So here I am stuck at the corner of Colorado and Nebraska. I think it's Julesburg or something. And I can't remember. I think it's like 180 miles or so. So you would say it's a 3 hours drive. So to be able to say that it's a 3 hour drive, or that I've been going 3 hours when I stop here for my latte, is assuming those same sets of assumptions. The constant rate, that I've been going that 60 miles an hour. And by the way, my foot is calibrated to 60 miles an hour because I learned to drive in the Jimmy Carter era, and that's what we had to drive. So if I'm not actually trying to go faster than 60 miles an hour, I automatically do. So anyway, so the constant rate assumption, the closed system assumption would be not too many lattes, right? You can't stop too many times along the way. And what's my third one? Help me. Closed. And then the initial condition and the rate. So initial condition would be that I actually, I guess, started when that's right. Started in Denver. Very good. So 3 different systems to think about the assumptions. So then this brings us to some really cool data that challenges some of these assumptions for some of the dating methods that are used conventionally with radioactive isotopes. By the way, radioisotope has nothing to do with playing the radio. The radio is just short for radioactive, which you probably knew, but maybe you didn't. So Dr. Russell Humphreys, I'm his fan. We both went to LSU. I don't know if that's why. And he's a physicist, so that could be why too. But he just thinks so amazingly that back of the envelope sort of stuff that physicists are supposed to do. Anyway, it's just an amazing contributions. Well, as part of the RATE project, he undertook to look at the content of some rocks, the helium content of some rocks. So these little stones are zircons, they're called. I'm wearing a zircon, by the way. Mine's blue. It was a gift when this RATE research first came out, and I was just astounded by it. My husband bought me a zircon. So it's radioactive, but uranium-238 is very stable, so I'm not too worried about the decays affecting my neck. So there were some samples that were obtained from granite, basement granite, Precambrian basement granite. These zircons are zirconium silicate. They are inside of biotite, which is that black mica-like stuff in granite. And they're inside of mica or biotite, and inside of them is little uranium bits. The fancy word is inclusions, little uranium inclusions. And so the uranium are inside of these. They're damage marks associated with the decay, the burn marks, like scorch marks, that are in these if you find them naturally, or you can cook them and anneal them all away. So mine's nice and clear blue because it's been cooked, so there are no defects in it that remain. The scorch marks disappear with heat. So what was the point of this research? Well, there's a long-standing problem, the helium problem, that all the amount of decay in the rocks should mean that we have more helium in the atmosphere than we do. And so this, where did the helium go? Did it escape the atmosphere? What happened to it? Well, that assumption is based on the helium migrating out of the rocks over geologic time. Helium is the second smallest atom, and it's a noble gas, so it's very inert. It doesn't like to react with much of anything. It's very slippery is the word that Dr. Humphreys used. It wants to migrate out of the rocks and get to the atmosphere. So why is it not in the atmosphere if the Earth is 4-point-something billion years old? It should be, but it's not. And Dr. Humphreys went questing for it in the rocks, and that's where he found it. Something on the order of 58%, upwards towards 58% of the helium is still in the rock. So that all by itself is telling you that the rocks are much younger. You don't even have to go any further, but there are ways of looking at this in a little more depth, which we'll do. So the radioisotope age, based on the uranium inclusions, uranium-238, has that 4.5 billion year half-life, which you don't have to wait 4.5 billion years to measure it, or we wouldn't know what it is, right? We can do and anyway. So the age based on the radioisotope uranium-238's decay was 1.5 billion years. But according to Dr. Humphreys' work, and he really didn't fake this. He really didn't. It's so spectacular. It's a big error bar, but still. He got a helium retention age, as he called it, of 6,000 plus or minus 2,000 years. So he had assumptions going on, too. He had to assume his rate was constant, which was diffusion. So you have to think really hard. What could possibly change diffusion in the recent history? Diffusion is kind of diffusion. So that's migrating stuff migrating through the solid. So he had the constant rate, the closed system, and the initial conditions as well. So something there's a sort of collision of ideas right here that we're going to have to wrestle with. So this couple samples of granite. These were photos by Andrew Snelling, also very much involved in the radioisotope rate work. So you see the black flecks. These are centimeters scale. There's always the compass, right? Always the geological compass for scale. And so the biotite flakes contain the zircon crystals. The zircon crystals contain the uranium inclusions, just to get that straight. And so now what in the world is this? This is our first halo. The uranium-238 halo. You can find in rocks these burn marks that are spherical. So your uranium inclusion sits right in the middle, and it's spraying out its alpha particles as they go off randomly in all different directions. Eventually makes a sphere. You cut it in cross-section, you get a circle. It's about 34 microns. A micron is 10 to the negative 6 meters in diameter. And you can count the rings like tree rings almost. And there are 8 rings in uranium. They call it a radio halo. And here is showing you the 8 alpha decays that take you from U-238 down to, it's not shown there, it would be a dotted product, lead-206, decay. So when you see this mark, you can no longer say the decays haven't happened. This takes about 500 million decays to get this fully developed, as they say, radio halo, to look like a sphere. Otherwise, it's just going to be one track this way, one track that way. It's not going to look like the spherical shape. So a lot of decay has occurred. There is absolutely no way around that. And the half-life at present day is very, very long. So this is kind of a daunting thing. So you would find these in the rock around the zircon. The zircon is small enough, or in the zircon, if the zircon is big enough, because it's the uranium speck or inclusion that's in the zircon that's forming this pattern. So here's just a schematic of a zircon. Should be blue, but they come in different colors. And here it's showing this spitting out of 8 helium atoms as you go from U-238 to lead-206. That's if you just really need to know what a zircon is. Zirconium sulfate. So, and here are all the decays in the chain to get you from uranium-238 to lead-206. And you get, there are the 8 heliums. And the others are electrons. Helium decays are called alpha because they were discovered first, alpha radiation. Electrons are beta, they were discovered second. Then there's a third, gamma, which actually will come into the picture maybe unless I run out of time. So there is our rate constant again. So you can do a half-life, or you can do a billionth life if you want. That's just the log of 10 to the billion. So it's again, this idea that you can measure this constant rate constant. It's not a constant rate, it's a constant rate constant. Over a much shorter period of time. You don't need to hang around for 4.5 billion years to measure it. That's just something that I think is confusing for a lot of people, so I'm going over it a few times. So then here is this beautiful result of Dr. Humphreys showing, so this diffusivity, distinct diffusion, because it's related, inverse temperature, so okay, 1 over temperature. But what he's showing is that based on measurements, data, of how fast helium diffuses through granite at a temperature, how does the helium that's left in the rocks stack up? And if you use a young Earth, the creation model fits it very beautifully, but what would be the deep time model is off, misses it, so the presumed result is off by a factor of 100,000 from the measured data, what it should look like. So it's really quite phenomenal. And it's from this that he is able to pull out that 6,000 plus or minus 2,000 years for dating the zircons themselves. So this 58% of the helium still left in the rock. If you don't understand anything else, that is just amazing. That's a lot. That's where the missing helium is, right? That's not like a few percent. That's a lot. So the most reasonable resolution is what's called accelerated nuclear decay. And why is it reasonable? It's way more reasonable to say there were short episodes when the rate constant, the rate was much faster. In the past, we would associate it with maybe creation week and the flood, one or both. That's much, much more reasonable than to try to argue how diffusion could be off over billions of years by a factor of 100,000. You know. So even though there are problems associated with accelerated nuclear decay, on the face of it, the one that's by far the more reasonable, the Occam's razor approach, is accelerated nuclear decay. So I don't think we should be backing off. And I hope by the end of my talk you'll see over and over again this is the most reasonable resolution repeatedly. So here is a slide I found on the, you can find anything on the internet, it's just amazing. So these two ideas of when you would have had these peaks of proposed episodes of accelerated nuclear decay. So associated with the flood, we have in our model as creationists, we have catastrophic plate tectonics also. Might there have been a coupling of some kind triggering the flood, accelerated nuclear decay, and whatever precipitated that catastrophic plate tectonics. And then there's another thing cosmically that Dr. Humphreys has suggested that we might pull in as associated with some things that would have been associated with the flood to bring on that Mammoth Judgment on the world. So now, I know I'm making you dizzy, because here now we have volcanoes. What if a volcano actually do anything?
Excuse me,
yes?
question. What is the explanation for what caused the accelerated nuclear decay? If that's causing other things, what caused that?
that would have to be, finally you have to go back, finally something will take us back to the first cause, which would be God. He brought the judgment of the flood, and he created everything. So, there does come a point where we cannot keep explaining things naturally. So, yes, Don.
In our kind of our Earth is a few miles or a few blocks away, I was reading their Foundation's newsletter, and they were talking about a theory where there's a huge piezoelectric effect in the, was it quartz?
Yeah, quartz.
Yeah, as you stress it. So like earthquakes, you see like lightning sometimes, and it comes from that piezoelectric effect. And a huge current can actually change one element into another.
Right.
So if the flood was loaded with a lot of catastrophic plate tectonics, that would be a logical explanation for why you would have had a lot of this decay going on.
Yeah, so that would put the source as the catastrophic plate tectonics of the accelerated nuclear decay. But then, of course, you have to figure out then what caused the catastrophic plate tectonics. I mean, but that's very, yeah. Now that's very interesting that stressing stuff does affect the half-lives of elements. I know. So, yes.
Yeah. When you mentioned that 58% of the helium is still in the rocks, how do you arrive at that number? Is there a simple explanation?
Well, I have not looked at the data that would support that, but it would be based on how many the evidence that we do have for decay. I mean, just counting the radiohalos of the uranium, for example. Okay. You can actually, if each one is 500 million decays, that translates into an amount of helium. And so, yes, there's definitely a gigantic approximation involved, but this was not a creationist invention, so that's a good thing to do. I'd like to go back and dig into the literature and find out, from a secular point of view, what they were basing the missing helium on, their estimates. But it's various ways. I mean, like, how do we have, even, I'm going to come to it in a minute, time permitting, oil reserves. How are those estimated? We do these really sweeping approximations based on what we can see to what we don't see. So, does that help?
I think I've got one of Russell's books I'm going to have to dig into.
Yeah. Yeah. Yes.
I think the fission tracks also corroborate the long age. That's an independent source.
The fission tracks
corroborates the long age.
Yeah. Right. I decided to leave that one out of today's. The fission tracks, you can add those along with the radiohalos to make an estimate of the amount of total decay. Yeah. The fission tracks would be those single jet lines of damage in the rock from just that one alpha particle, as opposed to when you see the whole bunch of them forming the spherical thing. And I'm looking at the time, unless you guys want to stay here until like really, really, really late. Maybe I should push forward.
I'll save this question.
Okay. All right. So, okay, now it decided to not go forward again. That is so weird.
What's the problem with the rate?
Oh, I don't know. Resume slideshow popped up. So now maybe it'll do it. There we go. Volcanoes. This is where we were. So here is one of the, it's called electron capture because the electron's on the reactant side of the nuclear equation. But you can sort of think of it like a decay. I think it's not put in that bin. But it is the nuclear reaction that's the Potassiumargon dating method. And I think most anybody who really knows has given up on this for dating any kind of, it's called igneous rock, so it's sourced from a volcano. It's cooled lava. And so here's this wonderful chart showing us the known ages of a bunch of volcanic eruptions and the radioactive isotope age. And when this happens, you throw away the method, because these are your knowns. And if your knowns are not corroborated by your data, then you can't use it on unknowns. And that's well established. But what I think is really interesting is that argon, like helium, is a noble gas. Argon, if it's in the magma, these are bubbles of gas, or maybe they're dissolved. And this is just my own idea, that the argon wants to come out of the magma, just like the helium wants to come out of the. That is the assumption that's been made. The helium should be in the atmosphere, according to the secularists or the scientists, but it wasn't. And here the argon is not supposed to be in the magma, but it is. So is it not telling us that the lava is young? Just like the helium in the rocks is telling us that the rocks are young, the granite is young. I don't know, what other source is there down there making more and more argon besides potassium, decay of potassium? I don't know. So that's just a little idea to think about. Just the fact that this method for dating doesn't work is telling us that the lava, all that magma, all that molten stuff down there is young, along with everything else.
Question.
So,
over here.
yes.
Oh, have they done that with Mount St. Helens?
Yeah, I think that was on there. Was it not? No, I didn't. This must have been before. Yeah, they've done it with Mount St. Helens. In fact, that's the next picture.
Oh, okay.
But because there it is.
Yes.
I anticipated you know it.
Yes.
I just lucked out. So this is a winter picture of the inside, the lava dome of the Mount St. Helens. And if you do potassium-argon method, you get anything ranging, just a small range of 350,000 to 2,800,000. That's just a small range. And we know it was in the 80s, right? I don't know the date, but I don't remember it. Somebody probably does, 1980 something.
82.
82. That was when I graduated. That was high school. So, anyway, so what assumption is the most problematic? There's my nice friend right here. Well, the uranium lead, if you're doing that as your dating method, then it's the constant rate. That's the giant question mark. That these episodes of accelerated nuclear decay being the only reasonable way to explain the presence of the helium. The others might be okay. With potassium-argon, our rate is a problem, but our initial conditions are also a problem. So maybe the bigger problem is the initial condition, the assumption that there's no argon in the lava, in the magma, when it's full of it. Okay? Because it was supposed to be in its molten state. It's supposed to degas, but it doesn't. So, and that's assuming a long time that magma's been around. And then carbon-14, which is the one we're coming to for the next topic, fossil fuel. Its problem is more the initial conditions than the rate. The rate is probably pretty reasonable.
Quick question.
Yes?
Isn't it true that a lot of contamination of that from the conditions is a certain level of water solubility, and so it leaches out some of the products so that you get a really distorted ratio?
Which, in the carbon...
Carbon.
Yeah, so probably closed system should be highlighted too.
Yeah.
There are probably some closed system issues for sure.
Yeah.
If I give this talk again, I'll make that one red. I agree. In fact, there's probably, how perfectly closed is any system? There's Mount St. Helens again, I don't even know why it's there. Except there's a lava dome, not in winter. And there's the before and after, and it's just kind of cool. I think it's misplaced. This slide was supposed to be hidden, but it's not. So fossil fuel is where I was trying to go, and there's the Sinclair dinosaur. Well, what was that we just heard recently about an oil well in the North Sea? They brought up a dino bone in it.
There was a core.
There's a
They cut a
core.
core.
They cut a core and there was a dinosaur bone in it. That's really funny to me because, there's a dinosaur with Sinclair. I don't know. That just made me really chuckle. So what is fossil fuel? Well, it's organic flood debris. That would be our understanding as creation science people, with the biblical assumptions that we base our forensic science on. So here, let me try to explain carbon dating. I just did this to my students, and they range in age from like 7th grade to 12th grade. It's really challenging. Some are babies, and some are in calculus. But we have these neutrons up here coming sort of associated with the sun, is the idea of what's called cosmic radiation. And they crash into nitrogen, which is 80% of our atmosphere, and nice stable nitrogen 14, and we destabilize it by adding this neutron, we turn it into unstable carbon 14. I don't do it, the cosmic radiation does it. And it kicks off a proton or a hydrogen also. So that is the generating mechanism for the carbon 14 in the atmosphere as we understand it. There are also things called nuclear tests that put a spike in the amount of carbon 14 periodically. In fact, it's one of the ways that you find out rogue nations that are doing nuclear tests they're not supposed to. You monitor the carbon 14 in the atmosphere as a ratio, carbon 14 to carbon 12, which is the dominant and stable isotope of carbon. So that's the source. So this is the pictorial, it's hitting the nitrogen, it's making the carbon 14. And then you have a respiration cycle, I don't know, some biology, I don't know biology very well, but between the plants and the animals and the atmosphere to where the ratio of carbon 14 to carbon 12 in the atmosphere tracks or matches the ratio in living organisms, whether tree or forest. So that the ratio of carbon 14 to carbon 12 in the atmosphere is paralleled in living organisms because they're breathing and eating and all. Maybe breathing, okay. And then they die, and if the remains are preserved as a fossil and not eaten by a coyote or something, or burned in somebody's fire, then these remains can then be looked at later, and you might try to infer how old they are, because once they die, the carbon 14 in them now begins to decay by this beta decay, gives off the electron, and reverts to nitrogen 14. So then this is the one that we're using to do the dating of it. So what do people do but go questing for things that they're not supposed to do, like looking for helium where it's not supposed to be, and now we're looking for carbon 14 where it's not supposed to be. It's not supposed to be in coal because coal is supposed to be millions, hundreds of millions of years old. All the carbon 14 would have decayed away because the half-life for this beta decay is only about 57, 30 years, 6,000 years or so. So what this data is just a bunch of, almost a lot of it is not just like more information than you want. This is the information you care about that tells the percent modern carbon in these samples, which wasn't supposed to be there. And this is telling you that you're spanning much of the geologic column, so-called Cenozoic, Mesozoic, Paleozoic, with Pennsylvania, Cretaceous, and Eocene, these geologic intervals, that's what that means. And so if you were to use the geologic column and the circular reasoning that goes into that to date these intervals, you would get geologic ages ranging upwards from, Eocene to Pennsylvania, 40 million to 350 million years. But if you find the date based on the carbon 14 content, you're getting 40 to 60,000. Still a big range, but not but it's tiny compared to this one, and the 40 is not associated with ESC and the 60 with the Pennsylvania. You'll see there it's all just on average the same. So all of the geologic record has the same carbon-14 content effectively. And that's quite remarkable. So when I say the entire geologic column, I mean everything Phanerozoic, everything above the Cambrian above, not below the Cambrian explosion. So just to situate you relative to our favorite geologic column field exercise is the Grand Canyon. And so we were in the Cretaceous, Pennsylvanian. Here we have Permian. I'm going to show my ignorance of geology. But anyway, just to realize that we're looking at layers of rock where the coals would be associated geologically. I'm not pushing anything more than that, just sort of a connector. There's the Pennsylvanian that would come from the sample. So and the assumptions are, so this is painful, I know, but I just have to show it. I just have to show it for those of you who care. So, what are the assumptions for going into this staging? Well, one assumption, that's what I did this the other day, because I wanted to come up with a formula. I'll show you my formula in a moment. Here's the exponential decay. I didn't make it as an exponential because I have e's running around for electrons, and I didn't want to confuse people. That's the e for natural logarithms, but anyway, that's just the equation for exponential decay. So to be able to use this to date something, we need to know this number. So how does it get massaged? It gets massaged into a ratio, and then assumptions are made, and about the atmosphere, and then this is finally what would be actually used, that you had to get there from here, from here, from here. So these are the assumptions. Modern carbon-12 content of the fossil is the same as the ancient carbon-12 content of the fossil. Because carbon-12 is stable, so it didn't decay away, so it should be the same. This is the closed system assumption. You've got to make it or you can't do anything. So even it might be imperfect, but you still got to make it, or you might as well just throw the whole method out. That's just saying that carbon-12 didn't decay because it has an infinite half-life. So that's all that's saying. And so the zero, F is for fossil, and 0 is for initial, if you want to know my numbers. The next one, the organism's ratio, carbon-14 to carbon-12, needs to track with the atmospheres. So I think probably this is what Libby, who got his Nobel Prize for, right? Recognizing this, because this allows us to do something. So this is fossil times 0, atmosphere times 0. Then finally, the assumption is that the ancient ratio is the same as the modern ratio. Now that's the big problem that gives those dates that are so long comparatively, even though they're short compared to the billion-year thing. So I was just enjoying reading stuff and thinking about this talk. And I ran across, or maybe I was thinking about teaching, I don't know what it was, an article by Dr. Snelling where he's trying to address the fact that secularist scientists were telling him, somebody was, that it would take at least 33 Noah's floods to generate the amount of coal that we see. And so I showed this giant coal seam in Wyoming. It would take at least 33 Noah's floods. And Dr. Snelling goes to some effort to kind of get this number down, because it's really at least, and it was like 33 up to 100 Noah's floods. Whereas I actually think he should just leave it alone. Let him think that it's perfect, and let me show you why it's perfect. You might have seen this slide, some of you, I don't know. So it would take 33 to 100 Noah's floods, you say. Well, the estimate to to make the carbon dates correct, because we know what they are, if you want to go with Usher's chronology, we know how old the rocks are when the flood was. So we already know, we know what it is. So if you want to back figure it, how much greater biomass, foliage, plants, animals, mainly plants, on the earth, did there have to have been to fix that 40,000 years and make it 4,000? Well, so this is just showing a graph that maybe it was. And the reason why it's suppressed, and it's really backwards, it's hard to think about this, it's because the C12 is what gets bigger. It's in the denominator of these ratios. So it ends up, you think, well, this should be high because the biomass is greater. But if we're measuring the ratio, and it's the carbon-12 that's greater, then the C14 to C12 ratio is a lot smaller. So that's where the bit of backwards thinking. I put Anno Mundi, like Usher has for fun for these days. So, anyway, so this 100 times looks an awful lot like that 100 times. What do they mean by 100 nodaless floods? It was talking about the biomass that got stripped off and turned into peat and then turned into coal. Why did I have that? That was left over from my class. This is a tombstone in Thessalonica that has an Usher date for the person's death on it. It's just kind of interesting. Anyway, it's a classical school, so we look for these things like Greek places to be classical. So then I got to thinking about this 100-fold, and I just got on, good old internet and dug up some fossil fuel reserve numbers from one's from Journal of Oil and Gas. The other was, I have it written down if you want to know. But the current reserves of the coal. This was just to get an idea of how much more than the 33 we need because we have more than coal. We have other fossil fuel too, like oil and gas. And so I found these numbers. TONNE, if you care, is a metric ton, so it's 1,000 kilograms. So you can. That is not adding all three of those. I see that's very, very confusing. That is adding those two, so I can get an idea of the ratio of oil and natural gas to the coal. And then you can do an equivalent energy for these things, like BTU equivalent, which might be sort of related to biomass. Because these are the numbers that were actually quoted because oil is in barrels and gas is in TCF typically. So that's a conversion factor I found on the internet. But then again, is BTU equivalent the same as biomass equivalent? I don't know. But it's something. It's related to carbon. So anyway, the 33 to 100 Noah's flood now becomes 54 to 163, putting 100 square in the middle. So now I understand that graph, if nothing else. Maybe some other creation scientist went through the same exercise. So the 100-fold pre-flood biomass estimate is square in the middle, which I think is cute. This is something marginally original. Otherwise, everything I'm showing you is someone else's work. And I also dug up for a map from 1950 showing global distribution of forest biomass. And so we have places where there isn't much. Not much. And the darkest green corresponds to something greater than 100. I just think that on the surface of our planet as is, you can have this 100-fold difference in biomass density. So if you had a greener Earth, maybe even less ocean, though I don't know, we were talking about ocean contributes a lot too because of all that algae. Anyway. So I did a calculation. I did a little math to figure out for any carbon age, what does that translate into in biomass? And so biomass is the factor of n. 1 would be the same as today. 100 would be 100 times today. Half-lives, and I had the standard versus what I would say would be the true because it's corrected for the greater biomass. And I was able to then understand, again, where the 100-fold gives the 42,000 years. And if you remember on the list of coals, the range was 40 to 60,000. So that's that carbon age that would represent, which is kind of in the lower of the range, but we do have issues of not closed systems and contamination, like gentlemen said. But I don't know. I think this is very fun. The 4370 is the Usher date for the flood. The 5730 is the half-life of carbon. There's the N, the 100. Log 2 comes from half-life. And anyway, I think it's cute. I think it's really cute.
And what is the 7.4 represent?
That's the number you need to multiply by the half-life to get the conventional age. So it's the relationship between the conventional carbon age and the half-life for a biomass of 100 times. That's the 7.4 is just what spits out. I can show you the math in greater detail if you want to see it later. I better move on, or I'm going to lose everyone. So now we're done with fossil fuels, and we're on to our next topic. Here we go to halos. It would seem that not only do we have parent and daughter isotopes in nuclear reactions, but we have parent and daughter halos. And this is really wild, and it's really hard to explain, and I'm going to give it my best shot. So here's the uranium halo again that we already saw with its 8 rings. It takes 100 million years to form. That's connected to its half-life, but remember, you don't need to wait a whole half-life to get enough to make a fully developed halo. And so this is the estimate from the literature, 100 million years to form at today's rate. And then there's another one, the polonium halo, that only has 3 rings, and it takes a few days to form only, by comparison because of the half-life being like 140 days for the polonium sequence. These 3 polonium rings correspond to the last 3 rings of the chain from uranium to lead. But you can see the uranium inclusion in the uranium radiohalos. There is nothing in the middle. And it's been a tremendous mystery for everybody. You say the polonium decayed away, but where did it come from? Because it's very short-lived. So the argument is this, that these, in the rocks, these tend to be just a few millimeters apart. And that this is very much tied to this, that, in fact, these are a bunch of the polonium decays that should have been over here, but the polonium, actually the one step earlier, the radon, migrated prematurely and took up lodging in the form of the next decay after the radium of the first polonium that I think, as if I understand the literature correctly, has a reaction with sulfur and you get polonium sulfide, which precipitates out and it gets stuck somewhere, and then that becomes a point where it's drawn and from the one site to the other. This is what I found in the literature to help with this explanation of this very complicated process. But you have the radon decaying, alpha decay to the polonium, and there was an A, if you wonder what it was. It looked just like that. It was like a summary. But otherwise, we're going this way in this sequence. So here is our little picture of our zircon. There's my zircon with its uranium inclusion, spewing forth its alpha particles every which way. And we have hot water flowing along the cleavage planes in the mica, in the biotite. The zircon's in the biotite, the uranium's in the zircon. And the radon is what can get transported. Basically, dissolves in the hot water. It's a gas. And it's spewing out its alpha particle, and when it does, it makes a polonium. And so now that polonium there happens to be some sulfur around, and the polonium and the sulfur get together. And so the polonium now is no longer moving through. You see these arrows, everything's moving through. Radon, it might still be making a polonium, but it's moving through because it's entrained in the water, but the polonium now is polonium sulfide, I think, gets nice and stuck. And so as this is spewing forth its alpha particles, finally it makes the radon. I hope I didn't just say radium. Makes the radon, that then makes the polonium, that attaches to the sulfur, and it gets stuck, and it's no longer moving, and it then forms its own radio halo nearby. But you would just think how impossible to stretch this whole process over for, the 100 million years it takes for that uranium, that extremely stable, almost infinite half-life uranium, to do this? Are these cleavage planes and this water all just going to stay there for, 4.5, for the 100 million years, so that we can have these alpha particles make their way to this same spot? It becomes just an impossibility. And then what's the thermometer going on here? That's about 300 Fahrenheit, 150 Celsius. Is back to the fact that my zircon doesn't have any damage in it to be seen because it was annealed, it was cooked. Well, so this hot water, it's associated with the cooling of the magma, that's the granite. It's not really magma, but it's cooling. And so that's why the temperature is getting lower and lower with all the slides. But when it's too high, that 150 degrees is the temperature at which any marks anneal away. So you can't get any halos in the rock when your temperature is above 150. So it's just, there's going to be no evidence of it. Until the temperature drops below 150, then you can preserve both halos. So if you have a fully developed uranium halo and a fully developed polonium halo next door, all this had to happen in this window of time when the granite was forming, crystallizing, and dropped below 150 degrees Celsius. But then you have a time constraint on the other end because the water is going to quit. So, because it's associated with the crystallization of the granite. So this is Dr. Snelling's graph to show this. We have temperature and time. And we have time in days associated with how fast polonium decays. And if the temperature is too hot, we get no formation of these marks to look at later in the rocks. And the water gets too slow to do anything. Gets locked into the crystallized granite. So you have this a few days. It means all of that decay of the uranium had to happen in those same few days that the polonium radiohalo formed. And the only resolution, there's my conclusion, which I'm going to have to make up. The only conclusion is, again, accelerated nuclear decay. It's the only explanation to. It's almost like these polonium halos right next to uranium ones. It's like a signature of accelerated nuclear decay. So instead of it just being the most reasonable explanation, it becomes a signature of it, almost definitive that it happened. And we're seeing in the rocks the episode, which is remarkable. It comes back even to the whole design argument, that over and over and over again we are able to see things that it's just astounding luck almost, or so it would seem, that we can even see them. Like God has made the universe such that it can be discovered. You know that. What's the great film on that called? Planet Earth? No, what's it called? You've all seen it. Privileged Planet. Gets at that. So this almost is an example where the right conditions only lasted maybe 6 to 10 days by Dr. Snelling's reasoning. So, and I have conclusions on the next page, so I'll just go there so you know that I'm just about done. But another thought I was having that I didn't get into the talk anywhere that isn't interesting is this connection between the systematic error out there in the radioisotope dating data, where the longer the half-life, the greater tendency for the thing to be dated older. So you can have different methods on the same rock, and the one with the long half-life tells you it's older than the one with the short half-life, which is telling you a problem with the known right there. They should all say the same thing. The same amount of time supposedly went by. But the longer the half-life, the older the age you get. And that, too, is a signature of accelerated nuclear decay. Because the more forbidden, quantum mechanically, the more forbidden a decay is, the greater the effect encounter of it is. So the uranium with its long half-life would have been accelerated way more than the polonium already with its short half-life, because the short half-life is telling you it's less forbidden. So if this ties back into quantum mechanics in any way, which is the work Eugene Chapman has done pointing to that, then this apparent systematic error that would say, well, it's all stupid, we just don't need to use it. Well, no, it's not. It's telling us something very significant, that yet another signature of accelerated nuclear decay. The fact that the data has the longer half-life tells you the thing's older. The shorter half-life tells you it's younger, systematically, when they should say the same age for the same object. I don't know if I made that clear. But I literally ran out of time. So I think I will close here and hope that you thought some thoughts that were new, or thought that were new, or thought about something a little deeper, and I would be happy to take any questions you might have.
You keep referring back to, and I've heard this before, this Jimenez Mountain site, where I think it was 1976 or something like that, that they, 74, they drilled a hole down and they came up with these rocks.
Yeah.
Is that the only place they can find this?
Well, I know that the radio halos themselves are ubiquitous, so it's not just in one spot. So presumably it's not the only place. But I think there was a little bit of luck involved in that data was available. The scientist involved was a Christian, and there was a connection. So I just don't think. I think it definitely should be done. I was having that same thought, but I'm sure it's money. We don't have any.
I keep hearing about that same site.
Yeah, because
so your perspective is that it's pretty much universal.
Yes,
but
right. But you want to test that.
But there may be some select spots where you have to get down to find the rock that has these right conditions. In other words, temperature and water. And,
yeah.
I guess those two conditions.
Yeah, I can't remember the article.
The right kind of rock, and then temperature and water.
Mm-hmm. Right.
Yeah, I think it's amazing that the temperatures were correct. All of those halos could have been annealed if it had been just a little longer.
Yeah,
that's right.
That's the privileged planet idea. It's
Well,
there for us to
was
see.
A blessing from God, right there.
Yeah, exactly. Like I said, the signature of accelerated nuclear decay. But I am totally with you. I'd like to see something more than. How do I say it? I kept saying Jemez. I know that's wrong. Jimenez?
Jimenez, I believe. The J is silent.
I will say it correctly in the future. Yeah, I was thinking that same thing. Surely we could do this. I think probably there's not the money to do it. So, yes, John.
Okay, yeah, so I only know enough about radiation to be dangerous. So when we see all these consecutive rings out from the decay, does one particular going from one step to the next give out a certain energy alpha particle?
Yes.
And based on the energies, how far it's going to go?
Exactly. I suppressed that for just, the case of TMI. But yes, in fact, I even put a little white box over it so it didn't look too numbery. But one of the slides shows those energies for each one. Okay. And that, in fact, is the gamma radiation we never got to. Alpha was found first, beta was second. Gamma is the fact that these decays leave the daughter nucleus in an excited state, not atomically, but nuclearly. The nucleus is in a quantum mechanically excited state, and when it decays, it gives off pure energy, a gamma ray. And that pure energy then is determining how far that burn mark is away from the middle, which is also just amazing. Yeah, that does bring me to.
And so the other thing is, okay, so as this uranium is decaying, if there wasn't the water flowing,
right,
that would have been like right there on top of the.
Right.
Of the
That's why it has 8.
Yeah.
Uranium always has 8 because it's not like every single decay is going to leave the center and go migrate to another place. right? So it's always going to have all 8.
But the fact that it's a distance away means that during this decay, it had to be migrating, and if this was millions of years to get from here to there,
It's ridiculous.
It wouldn't.
It's ridiculous.
Have gotten
Yeah,
it.
right.
So
you
that's-
wouldn't have that same little path
Yeah.
set up. Yeah.
So that's the argument for the use of that, right? Because the fact there's a polonium that's out there from here
Right.
that creates its own halo means that there had to have been flow.
And where would the polonium have come from? It's got such a short
And the right temperature.
half-life.
Yeah.
And the right temperature
Yeah.
for all that time.
Yeah.
Yeah.
Well, the gamma radiation thing brings us to what some might call the big problem of accelerated nuclear decay, is you've got all these excited nuclei decaying, putting out tremendous heat. I think Dr. Humphreys suggested it would like vaporize the Earth at so much heat. But it happened because we have the radio halo. So it's almost like that's telling us something dealt with that heat. It had to have. Because otherwise the radio halo wouldn't even form. Forget vaporizing the Earth. If you have the temperature is too high from the decaying, excited nuclei, then you wouldn't get them anyway because they peel away, right? So, and Dr. Humphrey's suggestion, which is that cosmic connection I mentioned to begin with, is that if you go for quantum field theory and you believe that space can be stretched, that a stretching episode would have absorbed that heat. And that would be a way, if you're looking for a way for God to have done it. So it's just the fact that, that's again the signature of accelerated nuclear decay, but we have this mystery of the gamma radiation, which is maybe the outstanding problem that remains. So, yeah.
Was this happening in solid rocks, or was this in rocks before they hardened?
They're hardening. Okay. But the radio halos, according to this creation model or understanding of it, would be late in the formation, in the crystallization of the magma into the granite, or crystallization of the rock into the granite. And that differs from the secular position that crystallization was stretched out over a long period of time. So,
and so does the heat that's being generated, does that account for the water temperature that you had to have? Started out as over 150,
and then coming down.
And then coming down.
That's it. I mean, if you think about nothing else as the rock is cooling, it's crystallizing, it's hardening, it's changing phases. Yeah. So, I've been trying to grapple with understanding this myself. So if I didn't give a really satisfactory answer, it's because I don't have a really satisfactory answer quite for myself either. I've read,
The other thing that is interesting is during the flood, we're told that the waters of the deep just cracked the surface of the earth and spewed out. And I would think that was very hot water as well. Any connection?
Not that I've thought about, but there could be. I've assumed that it's the ocean water hitting the ripped apart seafloor bottom that flashes the ocean to steam and made those supersonic jets. That's my understanding of the model of Dr. Baumgartner.
Yeah.
So maybe.
So when do we think that these daughter and and sons, I guess. We have
Yes,
parents and
daughters, I
daughters.
know.
When during the is the assumption that this process was taking place during the flood, after the flood, or as a result of the flood?
Well, you can locate it in a layer. That's where they're predominantly. I didn't get that point in my talk. I wanted it. You can locate it in a layer, and then you can build that into like Tim Clary's work and figure out exactly where you were in the flood. But I think it would have to have been very early in the flood year because everything else, I don't know though. I don't know. I mean, the slide I showed just put the blip at the flood. Right?
Yes,
It's such a short amount of time in the sweep of the thousands of years. So I don't know the answer to that.
On the decay path from uranium to lead, you've got a lot of steps in there. Is there exactly one path?
That's a good question. I don't know. I know that, like the argon, potassium-argon, there's actually two paths. There's one that instead of electron capture, you have a electron emission and go to calcium instead of argon. But that was when I read that, and again, too much information, so I didn't put it in my slides. But it said that was very rare. But I haven't explored specifically about that chain. But I know that having multiple branches that contribute to one half-life is rare. But it does happen. So there might be.
Yeah, the significance is.
But it only has the 8.
In your analogy, Denver to Des Moines, maybe there's a shortcut.
Right.
That really throws the timing off of how you calculate your time.
Yeah. Yeah, I'll have to look into that. I don't know about the other paths for each reaction. You'd think with all the ones that were involved, because it wasn't just the 8, it was 8 plus all the beta decays. But again, I think it's pretty rare. It's pretty rare to do either electron capture or electron emission. You just sort of have to pick. In the end, the reactions that happen are the ones that we observe. But I think I'm looking at the time, and I'm happy to take another question, but I have to shut myself down because this is the one-man show night. So I have to get my own hook. But another question, yes?
Just one more. As a side note, when you were mentioning about the trip to Iowa, as a visual on how the rate can be affected by the conditions around, think of yourself driving there in a blizzard.
Right.
And it gets you there in maybe 30 hours, And so we have no idea what the conditions are from the initial, when it was initially there to
right.
now. So.
Yeah, and so you have to bank on that closed system where you can't do anything. So you have to then just put a big error bar on everything as a result. Yeah, there's no question about it. Yeah.
But when you get like a sample, like with the volcanics, of something with a known age, you have concrete evidence. And so, that's awesome, because then you have to work back to that, because then you have a known age, and you have to figure out, well, how can we get this rate and stuff to fit into that? Because that's what's true.
Well, so they cried contamination.
Right.
But what is the contamination telling us? It's telling us that all this argon is still in the magma. That's what I think is pretty interesting. In fact, all the problem, carbon dating doesn't work. It's all contamination. Well, what is the contamination telling us? So. Well, we'll just go ahead and close, and so I'll switch to my other slide that has what I'm supposed to be doing next. Where'd it go? That's so weird. What's your problem? Why won't it come up? It's
When
right
the
there.
slide sits for a long time, that thing thinks it's not getting a new signal.
Well, but this one's not even coming up on my. Okay, I'm just going to go.
It's like you have to start the slideshow again or something.
All right. I'll go and just open the whole thing again.
Yeah.
So bear with me, if you would. Aha! Now I just need to get to go first. Resume. Yay! Okay, so these are the announcements. Now what are they? Okay, so, okay. Advertisements. The Rocky Mountain Aviation Fellowship having Mr. James Burr on some kind of astronomy topic. Littleton Baptist, right around TBD. Well, it's an astronomy topic that's to be determined. So that's Friday, October 13th, coming up. Be there. You swear or something, and there's the website. You can see it. It's a little dark. Denver.org. And then our featured speaker, we have Dr. Parker coming November 7th on natural selection versus epigenetics. He's also speaking at Lutheran High, and the Beautiful Savior, and the St. Mount Zion Adult Bible Study on the Sunday that would be closest to that November 7th, which must be a Thursday, I take it. Right? Is that our regular date?
Yeah.
Okay.
Where will the location be?
Here, unless presumably here. So I don't. All of our meetings are being here lately. So, and then the gentleman who was supposed to talk tonight, but then I took over. I think this is who, Dr. Frank Williams. Is that correct? So now he's our December speaker. He's the radio show person. Is that right? The Denver area radio show.
Real Science Radio.
Yeah, Real Science. I kept wanting to say Science Friday, but that's NPR. Real Science Friday. Real Science has a version of it. And information theory and the demise of Darwinism, so make note of that. Judy is at this conference, and then another conference also, so just keep her in your prayers as she puts the information about young Earth and the importance of it theologically in places in our church body. And if you want to make a contribution, there's the contribution information. We accept by the website.